Good morning. Today is Thursday, July the 23rd, and this is the first of 3 videos on Chapter 5 in your textbook, which is entitled Measures of Variability. All right, and this deals with such calculations as range, variance, and the standard deviation. In this video, we'll define each of these 3 things, range, variance, and standard deviation. And then we'll go on later in other videos to talk about how each of these things can be applied to something, for example, like the normal distribution. In Chapter 4, we spent a lot of time talking about measures of central tendency, the mean, the median, and the mode, all right, which are essentially calculations of averages of data. What variability shows us is how far apart, how spread the data are. Okay, you can have 2 sets of data with very similar means, but very different variabilities. So, our goals for Chapter 5 are to cover 5 essential things. All right, first, what is meant by variability? How far apart how spread out is the data range, or is the data? Is it spread out? Is it all clustered together? Does each individual score fit closely to the mean, or is it very far, or are they very far away from the mean? We'll talk about what the range indicates, all right? And the range is simply a calculation of the highest score in a data set minus the lowest score in a data set. That gives you the range. We'll talk about the calculations of standard deviation and variance, how to calculate them, and when they're used, and how to interpret them. And the final one here, how to compute the standard deviation and the variance when you describe a data set, when you describe the population, and when you estimate something for a population. Finally, we'll finish this chapter by talking about how variance is used to measure errors in prediction. All right, and what is meant by accounting for variance. Now, these are very important calculations because statistically they can answer very specific questions about a certain data set. As a matter of fact, the very first scientific paper that I ever published in a journal showed that my data set, my control versus experimental, had exactly the same mean, or at least not a statistically different mean, but their variances were very different, and that allowed me to actually justify my hypothesis. Okay, so let's talk then about what all of this stuff means, and we'll talk about new statistical notation here. Remember that the Greek letter sigma that you see here means the sum of, all right? And so let's say I have a data set that's 1, 2, 3, 4, and 5, okay? Now, if you add these up, and so this will represent my values of x. If I add these up, the sum of them is 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, okay? Now, the values of x squared are, of course, 1, 4, 9, 16, and 25, okay? And if I want to calculate the sum of x squared, it's 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, plus 25 is 55. So that's the sum of x squared. But the sum of x squared is 15 squared, and 15 squared is actually 225. So the sum of x squared is actually 225. All right, 15 times 15. Now, notice that there are three very different terms here: the sum of x, the sum of x squared, and then the sum of x quantity squared. Okay, so just keep those three distinctions in mind when we get into calculating the standard deviation and the variance. Okay, so measures of variability are used to describe the extent to which scores in a distribution differ from each other. What they really are talking about is how consistent is the data across a data set. How accurately is the distribution described by the measure of centrality, in other words, the mean, the median, or the mode, and how spread out the distribution is. So, for example, if you have a data set that's 1, 2, 3, 4, and 5, all right, you know that the mean of this data set is equal to 3, right? If I add these up, I get 15, divide them by n, and I get 3, all right? However, if I have a data set that is 2, 2, 3, 4, and 4, all right, the mean again is 3, all right? But if you look at these two data sets, you can see that the first one, the top one, is much more spread out than the bottom one, okay? And there's a difference in the range, the variance, and the standard deviation. We'll get to that and how to calculate that in a few minutes. So these measures of variability talk about not only the measures of central tendency, the mean in this case, but they also describe just how spread out the data actually is, all right? How spread out the distribution is. Now, let's have a look at this graphically so that you can really see what these numbers look like. We have three samples here: sample A, B, and C. And in all three samples, the mean value is 6, all right? If you look at sample A, 0 plus 2 is 2, plus 6 is 8, 18, and 30. 30 divided by 5 is 6. If you add 4 plus 5 is 9, plus 6 is 15, plus 7 is 22, plus 8 is 30. 30 divided by 5 is 6. 6 plus 6 is 12, 18, 24, 30. 30 divided by 5 is 6. So the means for all three of these data sets are the same. There's 6, okay? But obviously, I mean, just by looking at the data, you can see that sample A has data that is much more spread out than the data that you find in B, and certainly more spread out than the data you find in C, right? C is consistent, very consistent, all right? As a matter of fact, there's no variation at all in sample C, whereas there's a tremendous amount of variation in sample A, okay? The blue arrows that you see at the bottom of the screen here and here and here represent the range of the data. Notice that in sample A, the range extends from 0 to 12. In data set B, it extends from 4 to 8. And in data set C, the range is just covering 1. Okay, and so obviously sample A is much more spread out, much more much wider, and sample C is far more clustered than the others. Okay, so how do we then use this in order to calculate variations? Well, before we do that, let's talk about the normal distribution. We've talked about this a few different times, and this slide illustrates three normal curves, all of which have a mean value of 50, okay? 50 is obviously the most frequently seen score in each of these data sets, but if you look carefully, you can see that distribution C is much fatter than distribution A. And what that indicates is that the range and the variance and the just overall variability of data set C is far greater than B and especially than A. And so the data is more spread out. I wish, honestly, that the slide had done this backwards and kind of used the data set in the previous slide to illustrate this. But this distribution, C, would be representative of the first data set that you saw in the previous slide. And A would be representative of the last distribution that you saw in the previous slide. But in any event, the variation here obviously is only that big. But in sample B, or distribution B, it's bigger. And in distribution C, it's even bigger. All right. And so there's a wider range of data in distribution C than there is in distribution A. Okay. So that brings us then to the actual math involved in calculating the range, the variance, and the standard deviation for each of these data sets that you might have a look at. Okay. So let's start with a discussion of the range. Now, the range, it simply indicates the distance between the two most extreme scores in a distribution. So what you do is you find the highest score and the lowest score, and you take the difference between them. Okay. Now, if you go back to the data set that we saw a couple of slides ago, or the data sets that we found used a couple of slides ago, in that first data set, the highest data point was 12 and the lowest was 0. So the range for sample A would be 12. 12 minus 0 is 12. For sample B, the highest point or data point was 8 and the lowest was 4. And so the difference there is 4. 8 minus 4 is 4. And then finally, the sample C, the one that was all 6s, well, the highest value is obviously 6. The lowest value is 6. And so therefore, 6 minus 6 is 0. The range in that sample C would be 0. Okay? And so, again, a very straightforward calculation. Nothing too difficult there, I don't think. All right, but that's how you would calculate the value of the range. Okay. Now, unfortunately, the calculations for variance and standard deviation are a little bit more complex. So let's start by talking about them first. All right, variance and standard deviation. Let me get my ugly mug out of the way here. So when the mean is the appropriate measure of central tendency, all right, which it often is, we can compute the variance and the standard deviation to describe variability. Okay? Remember that the mean is the appropriate measure of central tendency for normally distributed interval or ratio scores. Okay? So if you've got an interval or a ratio score, the average, the mean, is the best way to calculate the value of central tendency. And if you're going to use a mean, then in order to describe that data set further, it would be appropriate to use the variance and the standard deviation in order to describe the distribution of data around that mean. Okay. So that leads us to the actual calculations of variance and the sample standard deviation. Okay, these are actually two different calculations, although you'll see in just a second that they are very closely related. So let's start with the variance. The sample variance is the average of the squared deviations of scores around the sample mean. Okay? The formula is S squared equals the sum of the difference between each data point and the mean squared divided by the number of data points in the sample. Okay, so sigma parentheses x minus x bar squared all over n. Okay, and so this is the formula for the variance. And we'll do some sample calculations of this in either video 2 or 3, depending on how this all works itself out. All right, but that's the formula. Write that down somewhere because you'll need it for your homework, your quizzes, and that sort of thing. So keep this formula written down somewhere. You should actually probably also write down the range formula as well. Okay, so take a second and write that down, please. And I'll have a sip of coffee. Okay, so what's the difference then between this variance and the standard deviation? Easy peasy, my friends. All we have to do is take the square root of both sides of this equation, and we get the standard deviation. And so the sample standard deviation is simply the square root of the sample variance. Easy, right? And so in this case, the defining formula is simply S equals the square root of the sum of the difference between each data point and the mean squared divided by n. All right. So the formulas are obviously very similar, but there are appropriate uses for variance and for standard deviation. We'll get into that, when to use which one, a little bit later on. In reality, the standard deviation is typically the more useful of the two calculations, but notice that you need to calculate the variance in order to get the standard deviation. Okay. So what's the difference between the two then? Well, the standard deviation communicates the average deviation from the mean. Okay. Meaning how far is the average data point from the mean of the data set. And so it illustrates the consistency of the scores. How close is each score on average to the mean score, okay? Which tells you essentially how spread out the distribution is. And of course, if it's a normal distribution, does it mean, is it a very narrow distribution, a very tall, pointy normal curve, or is it a wide, fat normal curve? Okay, so that's what the standard deviation is really all about. All right, finally for this video, for any roughly normal distribution, the standard deviation is equal to about 1/6 of the range. Okay, the standard deviation is about equal to 1/6 of the range. And we'll talk about that, and I'll show you some illustrations of this at the beginning of the next video. So that is the end of video number 1 for chapter 5, and I hope you learned something.